Hi, good morning. Oh, guys, I slept at 2 last night. I was gonna sleep at 10 and then I stay on my phone till 2. I just don't. I'm very disappointed in myself. Really, really disappointed. Really, really disappointed. So I think what I need to do is just like, past 10, I just have no self control. So I just need to make sure that by 9:30, like if I want to sleep at 10, I need to really settle down at 9:30. Like really not be strict with myself. Because by 10 I'm like, oh, it's already 10, and then like it takes that, and then like I settle down, it takes like till 11. Okay, okay, we're gonna make sure we do that today and every day. But today we're gonna finish up what I was doing yesterday with the SayCan paper. There's some implementation details that still were not clear to me that I wanted to ask. So first thing I think is afterwards I read a bit more. So they talked about like prompt engineering. Uh, so so what happens is like we usually when you use an LM, it's like kind of auto-regressive where it just generates text, right? But here what they do is, there's only a set of skills that the model knows how to do. So for example, what are the skills? Finding an apple, finding a Coke, finding a sponge. Each of these are different skills. Um, I guess finding, how do they develop the finding skills is interesting. But at least like pick and place, it's kind of obvious like what it can do, right? Or like, but so I think what happens is they, instead of letting the LLM run wild and generate any task, any text, we just give it a set of options and then we score these based on how likely the LLM would generate these. Yeah. And I guess like these numbers are like log likelihoods. Is it just logits? Like how is this? Yeah. Note here, up here. The end cases. Oh, how do you what does this mean? Yeah, something. Yeah, scoring. Given a set of low-level skills by the language description and instruction I, we compute the probability of scoring a model over potential completion. Right. So just taking the argmax. Right. So okay, that's basically what I described. Is taking okay, we're taking our logic values, and then what we'll do is we will create here is that we can fix the set of outputs by the LLM to discrete skills that we want that we know the robot can do, as opposed to let the LLM run wild and generate any token it can generate. If you did that, you need a way more sophisticated way to how the token a particular skill. Okay. So two, after you do this LLM generation, you want to do action grounding, or what do they call it? Or afford grounding. So they want to ground it to the value function. I think actually the appendix is like more helpful. Which is aware of the location, where yeah, okay, I think this is really interesting. They actually create kinds policies. For different kinds of skills. Aware of the location. Aware of the This is interesting. Thought reasoning. Table 4. That's it. So Jason Lee is at Meta now, right?
Might see some sentence, the word for pretty in Spanish will be 0. And then the accuracy suddenly starts to improve. So you can define like an emergent ability basically as for small model.
Hard to take, but that is, I think, really important to encoder-decoder architecture. Last one,
So again, I'm very happy to have Jason here. So he's an AI researcher based in San Francisco, currently working at OpenAI. He was previously a research scientist at Google Brain, where he popularized key ideas in LLMs, such as chain of thought prompting, instruction tuning, as well as emergent phenomena. He's also a good friend of mine, and he's been here before to give some talks. So we're very happy to have you back, Jason. And take it away.
Great. Wow. Yeah, thanks for the intro. So a bit about the structure. So I'll talk for around 30 minutes, and then I'll take a few questions, and then Kyung-Won will talk for 30 minutes, and then we'll both take questions at the end. Great. So I want to talk about a few very basic things. And I think the fundamental question that I hope to get at is, why do language models work so well? One thing that I'd encourage everyone to do that I found to be extremely helpful in trying to answer this question is to use a tool which is manually inspect data. And I'll give a short anecdote. I've been doing this for a long time. So in 2019, I was like trying to build one of the first lung cancer classifiers. So like there'd be an image, and you have to say like, okay, what type of lung cancer is this? My first thing was like, okay, if I want to train a neural network to do this, I should be able to at least do the task. So I went to my advisor and I said like, oh, I want to learn to do this task first. And he said, Jason, you need like a medical degree and like 3 years of pathology experience to like even do this task. And I found that a bit discouraging, but I went and did it anyways. So I basically looked at like the specific type of lung cancer that I was working on. And I'd like read all the papers on like how to classify different types. And I went to pathologists and I said, okay, I like try to classify these. What did I do wrong? And then what do you think of that? And in the end, I learned how to do this task of classifying lung cancer. The result of this was like I gained intuitions about the task that led to many papers. Okay, so first I will do a quick review of language models. So the way language models are trained are with the next word prediction task. So let's say you have a sentence, Dartmouth students like to. And the goal of next word prediction is you have some words that come before and then you want to predict the next word. And what the language model does is like study language model is going to put a probability over every single word here. So like, you know, the zucchini is the way that you train the language model is you say, I want, let's say drink is the correct word here. So 1, actual next word. And you want this loss to be as low as possible. Okay. Is like this number here, 0.6, to be as close as possible to 1. So your loss is like basically how close is the actual word, the probability of the actual next word. And you want this loss to be as low as possible. I encourage everyone. What I mean by this is the following. I'll give a few examples. A language model on a large enough database, large enough data set, on this task of next word prediction, you have a lot of sentences that you can learn from. So for example, there might be some sentence, in my free time I like to, and the language model has to learn that code should be higher probability than the word banana. So it'll learn some grammar. It'll learn lexical semantics. So somewhere in your data set, there might does not go like that. Okay?
The
language model abilities are real. And if you think like, yeah, I guess I don't think that's a mirage. So yeah. Yeah. Whatever your research project is, before the
thing, and then try to incorporate that into some kind of mathematical model, encode this into a dense vector. So here I'm representing differences. We'll see each of the attention mechanism. And
Hi, thank you for the talk.
Today I'm interviewing Steve, an ex-Amazon principal software engineer, which by the way is a level only 1.5% of engineers reach to. He spent 18 years at the company, did over 850 interviews, and even helped set the hiring standards at Amazon. So today we're going to be pulling back the curtains, exposing everything that you need to know to get hired in this crazy competitive tech market.
That is, you've reached on like, don't put it in sentences. They're really easy to digest. Because if you think about what a recruiter or hiring manager is doing, they're quality.
one example is machine translation.
Okay. Well, didn't learn shit. Let's read this chain of thought paper. Yeah, why are they, I mean, we know what chain of thought is. It's just like it reasons for tokens. How is chain of thought trained, I guess, is what I don't understand. Yeah, it's just like giving chain of thought examples, right? Yeah, okay, got it. Okay, so SayCan just does chain of thought. Are they tried the ablated chain of thought. Yeah, I guess the way the affordance is trained is also interesting. The value function. Yeah, for the affordance functions, interesting. Interesting. The pick go to affords are actually basically manual features, which actually looks like a hack. Like, it's actually not that complicated. It's just this value function for pick. Yeah, the pick is just like a value function. Which is really interesting. Okay. And go to just the navigation policy. For navigation, But it's like integrating all of these together is the hard part, and I guess they figured this out. Okay, interesting. So let's answer some of these takeaways, right? What are the authors trying to do? Find a way to leverage the LLM, which is really good semantic understanding language, and acquire and use them to control for in long horizon tasks and which and policies that are only trained on specific skills. The picking, moving, and navigating, right? So you have these different policies, you need to switch between them, but you need to connect this to a high-level LLM. So to figure out which actual step you need to do, yes, you can just have your LLM say which one and just execute it, but in practice you also want to ground it. Good question. In addition to plugging the LLM to the actions, the policy directly, you also want an intermediate step to ground the actions generated by the LLM before saying, yeah, this is we actually want to do. Okay. Prior work. I don't think people in robot learning were not really using LLMs, yet they had they train specific skills, not able to complete long horizon tasks. Like if you think about it, like almost is actually quite simple. You know, you'd think like, oh, there's parts that are like all that, it just takes time to understand what they're doing. Once you understand what they're doing, it's really not that complicated. Alright, like you understand what an LLM is, you understand how an LLM works, you understand like, okay, what a policy is, you understand how their policies are trained to these individual things, then you just need to like understand how to connect these together. Like the LLM, you don't use it the way an LLM is generally used, you just fix the potential output tokens and you look at the probabilities that the element would have generated this, take the max, ground it through some scoring function, and grounding it is really important because if you just don't look at that, it's not, you know, they run it in physical robots and check success rates. Alright, what are some limitations? Like I think the hand engineering the affordances. Okay, RL training and policy. ResNet. ResNet again. Okay. SayCan parameters. Multilingual queries. Yeah, where are the limitations? They mention. The underlying skills, still the fundamental limitation. The high level, I think, is actually quite easy. Yeah. Okay. Okay, that makes sense. Okay, and we should look at DreamerV4. Oh my gosh, DreamerV4 came out, guys. DreamerV4 came out. Oh my god. To be fair, I haven't even read in depth DreamerV3. Okay, wait, I need to still recap SayCan, right? So like SayCan came out in 2022, and then right after like Google shut down, and then they sort of moved to like robot foundation models, right? So before they would have this two-stage thing where you have very high level, you just use an LLM to do the planning, but you need to have it grounded. So you just ground it to this like dot product, and then it's sort of like a multiplexer where you select the right you're given a set of skills, right? And so it's like very discrete, but how do you sort of like get more general purpose robots that like you want to train on more skills, and you actually want to train it end to end, right? And so then you just train like you train a robot foundation model that's can do, it's like one policy does everything for at least pick and place, and it is conditioned now both on image and text, or it could be, and how would the setup look, right? So you ask, how would I, in the same setup, I want you to find, like, I think it's still, you still need this because our current robot foundation model still cannot do navigation, but perhaps pick and place can be one policy. And they're more capable, and so you would do the navigation. You still need like the high level planner. It would be a separate model. Yeah. I guess that's an open question, is like, how do you do navigation in one model? It's not so clear, but I think we have more capable models now, and so I think like if you redid SayCan, you would actually have like much higher success rate. Now, in terms of like the high level planning, like I think like the grounding with the dot product is kind of a hack, right? Like really, your model should really have a better understanding of what it's capable of. And so, I mean, you already limit what it can generate, right? So it kind of knows what these different tasks, but I don't understand why it's not grounded. Like, I guess like, yeah, why? Wait, let me close my camera. I need to. Like, why is it that they need to do the grounding? Right, like this is sort of key, like where are the failure modes, right? So like finding a sponge, I would go to the table, alright, so I would pick up a sponge. I guess the main failure mode is here. It seems like I was confused, like how much of grounding is actually necessary, because the LM should already be restricted to generate actions that the robot can already do. This seems Mostly like find before it pick up. No. People are still working on. Okay. Yeah. What's been done?
And work that went into it obviously depends on how you spell. So will be pick up sponge and so on. It needs to navigate around slowly. Yeah, but still, these are, I think, limitations that can be overcome. Look how he like carefully grabs. And yeah, in any case, there are also a lot of good things right here. And I want to highlight that because what I really like about this is that these two things are disjoint. So the language model side on the left-hand side and these value function, this policy bank, these atomic actions, they are disjoint. The language model is not trained. It is a frozen language model. It can be trained completely in isolation to this system. All you have to do is get it to score the likelihoods of some actions. Likewise, the bank on the right here, it is completely, in fact, not the bank itself, but each individual skill, each individual entry is trained completely isolated from all the others. All you need to add a new skill right here is a policy that can execute that skill at any given moment, and a value function that estimates, given some state input, that estimates how likely the policy is to succeed if this action, if this policy were to be executed at this particular moment. That's all you need. You can add this to your bank of actions, and you don't have to retrain anything in this system. It is directly useful. So you could think of shipping out these robots essentially and then upgrading the language model so they are better at planning stuff. Or you could just ship new skills, right? It's like, well, our coders have developed some new skill for the robot, right? You just mend it. You just put it in. You don't need to update the full system. This is not an end-to-end system. And usually in deep learning, we're quite end-to-end happy. But in this case, I think this is a really good case where modularity is really the key. I think this goes so much beyond just robots and grounding in the real world. But to have a model like on the left that has knowledge about semantic knowledge, high level knowledge, and so on, sequential knowledge, essentially, to provide that with a set of modular pieces of external things that it can use, I think that idea is powerful way beyond just the robotics use case. But obviously, the robotics use case is quite a cool one, so I don't want to discourage that. Yeah, in the interview we go into all of this. We go into the experimental results as well. The experimental results are not perfect. However, they are quite impressive in that the robots, they are able to plan across many, many time steps. They're able to chain these actions. You can see on the right here, that's maybe 2 pixels, but these are like 17 of these atomic actions that are done in sequence. And, that's quite impressive. These episodes are very, very long. And if you think you can get to that in the real world with sort of a reinforcement learning approach, then good luck. Yeah, so the success rates are among the 70%-ish of planned success rates.
Inner monologue, which is embodied reasoning. guess like we can look at hopefully robotics research. Hello. Hmm. Maybe these robots are still around. Oh, there's so many papers. Yeah, I think like I think it's not too bad. Oh, keep mine. Okay, RT1, RT2, and like auto RT is kind of cool. Yeah, there's actually many like I think actually many scaling. But I heard your infra is not the best. Or like it's so hard to do stuff. And Jason looked at VIP was like at Meta, but really interesting. It must be like the same angle. Yeah, but like yeah. Let's see.
RoboCat is a foundation agent for
Is that all? Seems mid. Seems mid. Okay. Anyways. Cool. Look. Add a note here. That's crazy. I would love to enter a deep line. penetrated through Google. That's crazy. Okay. No. Nope. There's not that many viewers, but okay. Go. Acquire. Dennis. Good job, Dennis.
Environmental feedback in this work. Embody reasoning through planning with language models. Imagine the thought process when a person tries to solve some task. I have to unlock the door. Let me try to pick up the key and put in the lock. No, wait, it doesn't fit. I'll try another one. That one worked. Now I can turn the key. The thought process in this case involves choices about the best immediate action to solve the high-level task, observations about the outcomes of attempted actions, and corrective actions that are taken. Recently, it has been observed that large language can embody agent like a robot plan actions with semantic feedback for such tasks. Recently, it has been observed that large language models can generate coherent action plans for complex long-horizon tasks, even without any additional training. Specifically, when they are prompted with examples, they can be made to produce sensible action plans for new tasks, such as bring me a drink from the table. To ensure the produced actions correspond to the existing skills of the robot and are grounded in the environment, prior works propose several techniques, such as semantic translation, action scoring, and leveraging affordance functions of skills. However, what if an action fails during execution? What if the robot needs to replan the future actions because the scene has changed? We propose inner monologue, a method that informs embodied feedback with language for interactive planning in dynamic environments. Given a high-level instruction, instead of having language model generate action plans without any chances to make corrections, we propose to continually inject information into the language model prompts as the robot interacts with the environment. For example, we can provide descriptions of what objects are present in the scene. Language model prompts as the robot interacts back using heuristics. Importantly, the entire process only requires few-shot prompting and no additional training during the first step and the third step, and it was able to issue a retry. And this task here is to put the bottles and the fruits in different plates. Without being trained on this task, the language model planner produces a correct plot. In this interactive setup, the task is to throw away the snack on the closed counter. The robot first goes to
Okay, place could be useful. Station. I mean, it's just dog shit that it's not open source, right? So.
Can pre-trained language models plan actions for embodied agents, even without further training? Given an arbitrary human activity, such as put away groceries, we desire a complete action plan. Those are large enough, achievable by the agent, but their executed phase, and many more. Thanks for watching.
It's so funny. So we went to U of T. Oh. This is one guy. Hmm? I feel like this is fake. This paper is sort of like along the lines of things I think about. this? Yeah, whatever. Don't want to add that. I still don't get affordance. Is it like how feasible something is? Like sorry, not interested.
To avoid
Avoid
acute
acute pain.
in order to avoid acute pain. And so people would much rather lose slowly over 5 years
Yep.
than have the conversation that involves.
No thanks. No thanks. Who is? No thanks. Just mute.
Another episode of Robo Papers. Today we're super happy to have Kyle Perch and Pranav Atria, who are CA and policy
Maybe not.
Robo Papers.
Okay, alright, let's go over Dreamer and then wrap it up. But we spent some more time surveying Google's papers. Yeah, perhaps I'll push back DreamerV4 tomorrow. Because I need to do school, I need to ship. And I need to get access to Gemini. I actually have access to Gemini. I guess just like set up the API. Yeah, this guy did. looking. Wait, it has not been updated in so long. Okay. Okay. Alright, I will continue this tomorrow. Alright, see you guys. Hopefully tomorrow I'll be up at 6:30. Which means I have to sleep at 10. Which means I need my lights to be red by 9:30 or 9. Needs to be on by 9. How do I schedule? How do I schedule?